them to help you advise. And here we go. And there's also a video on Kinematics, good, that you could use. So recall, first of all, that if you have a model for displacement and you drive it, you get velocity. If you drive velocity, you get acceleration. That's the main premise of kinematics. But there are some finer points that I need to talk about. So here are some important points. Firstly, one-dimensional math methods. We'll never deal with anything beyond one-dimensional. Specialist math students are doing it to do with vectors, which are 2 or 3D, but you only have to worry about one-dimensional kinematics. So singular functions that represent a one-dimensional movement or velocity or acceleration. Velocity is equal to the dx dt, that's a technical term, but this can also be written as x dot or r dot. Dot is more of a physics term, but it can be used. It does come up every now and then. I'll send it a couple of times in the textbook. A can be written as x double dot. So A is the derivative of velocity. It's the second derivative of displacement. So just be aware of that. There's some definitions for you. O is the origin. If we ever talk about point O, it always means the origin. So see that, but just make sure you don't get it confused with 0. And here's some definitions that you should already know, pretty much. I'm just reviewing most of this. So the definitions is that in terms of displacement and distance, there is a difference between those terms. So again, let me just show you more visually. Displacement represents how far I am from where I started. So if I walk around here like this and end up back here, I'm now about 20 centimetres from where I started. So my displacement is 20 centimetres. But the distance I travelled is this distance the whole way around. It's something more like 2 metres. Displacement and distance are different. The model that you will get is really good at representing displacement. It'll represent how far you are away from the centre, but it won't accumulate a distance. So any model you get is typically going to be displacement. Most questions will be to do with displacement, and a lot of contexts require you to work with displacement. Some contexts, though, require you to work with distance, so just be careful. And there's an example. So I'm going to talk, we'll just fill these in now, and we'll do it again for the next one. So in this example, I'm trying to show a one-dimensional movement, but I've got to have a two-dimensional line there a little bit to show it. Somebody starts at 0 at the origin, moves right out to 7 units, meters, and then back to 3. In this situation, their displacement is only 3. They've gone from 0 to 3 overall. But their distance is 0 to 7 and then back to 3. Which I heard 10 on this one. So 11. I believe it's 11. 7 plus 4. So we've got 3 and we've got 11. Does anybody have any questions on that? Because you've gone out from 0 to 7 and then you've gone back to 3. So the distance you've walked is 11 metres. Yeah. Your displacement is how far you are from the origin, which is 3 metres. I'm actually with Kira because I made a very clear point of explaining that I'm trying to represent one-dimensional, but I had to put in two-dimensional for my diagram to work. Yourself minus 7 marks from Harry's next exam. Okay. Velocity and speed. So the rate of change at that point is represented as dx dt, and the speed is the magnitude of velocity. So the speed is basically just velocity where we don't care about direction. Now, in one dimension, speed and velocity are really similar and you don't have to do much work. Basically, in one dimension, if I'm travelling at 5 metres per second this way, that looks like this. If I'm travelling 5 metres per second in the other direction, I've only got 2 directions, and that looks like this. My velocity is either plus 5 or negative 5. My speed is just 5. Doesn't matter which direction I'm going, speed is 5. And you go back to that common example of driving a car. You might talk about velocity with certain things, particularly if you do physics. But if you're driving a car, you're going 60 kilometres an hour in some direction. we never actually think about and we don't say, oh, I was traveling 60 kilometers an hour west, and then I was traveling negative 60 kilometers an hour when you're going east. You don't do that. So speed is just a number, and we don't have a negative associated to it. In one dimension, speed will just be the absolute value of velocity. So if your velocity is -7, well, your speed is just 7. So it's not a big change. Don't have to worry too much about that. On the other hand, the average velocity and average speed is a bit of a change. And we've got that diagram again, so I'm sure someone over here is going to complain about what I'm about to say. But the average velocity, this is where, and you've got to be really careful because this is the mistake a lot of people made in their exam last term. Velocity is an instantaneous rate of change. It's the derivative of displacement at that exact moment. Whereas your average velocity is where you start looking at your gradient over time. So you get your starting point and your finishing point, and you look at the distance travelled and the time it took, and then you can work out your average velocity. But velocity, remember, is your change in position, which is displacement. Speed is the distance travelled. So going back to this question, you remember that my average velocity is displacement over time. What did I say the time was? Time, I don't know. So let's just say time taken equals 2 seconds. The displacement is 3 over 2 for time, and that's equal to 1.5 meters per second, or whatever the distance unit is. So I've travelled, on average, in the first second I travelled 1.5 meters, and the second I travelled 1.5 meters. That's my velocity. My speed, on the other hand, is the distance travelled, which is 11 divided by 2. So my speed was 5.5 meters per second. So to make this total journey, I had to travel at 5.5 meters per second because I had to go all the way out to here in the first second and then back around to here in the second. So in terms of something to do with actual motion, say a car, you're probably going to be working with speeds more for that reason. But obviously representing this as 1.5 meters per second doesn't make sense for a lot of movement-based contexts. But if we only care about the overall big picture, you started here, you went to there, more sense. So just be wary of that. And you might also be asked to work out average acceleration, So if your acceleration is the step up from velocity, there is no distance-based acceleration, they're the same. And average acceleration is between 2 points, so it's an average rate of change, AROC. And acceleration is an instantaneous rate of change. So if you're asked to find the average acceleration, you'll find position or your velocity at this time and your velocity this time, and then do the gradient. If you're asked to find the acceleration, you'll just find your velocity at that point in time and substitute the time into that function. Again, 99% of the time in math methods, we're just dealing with acceleration. That really comes up. But it's there, it might come up in the textbook, I want you to see it. Here's a little language thing, and this will be important for your PSMT. In terms of acceleration, if your acceleration equals 0, that means that you are not speeding up or speeding down, or slowing down. That means you've got constant velocity. So an acceleration of 0 is constant velocity. If your acceleration is greater than 0, then you're speeding up. So your rate of change is increasing. If your acceleration is less than 0, then you're slowing down. Your rate of change is decreasing. So in your PSMT, the use of the words increasing and decreasing can be really effective, but you have to get them right. So you just got to make sure you're very thoughtful about your use of those words. And I've got 2 examples, and I'm going to leave you alone. Example 1 is really, really theoretical. There's nothing there about the context at all. I'm just asking you, if a particle has x equals 2, v equals -7, and a equals 3, describe what's happening to this particle. Reggie, what do you got? Anybody got anything? Okay, so it's at the moment, it's 2 meters from the starting point. So if I put O here, it's currently sitting there at 2. So that's where the particle is. And what's the particle doing, Pascal? It's decreasing. Okay, so the distance is decreasing because we're at 2. So there's lots of ways you can describe this. We're at 2, but we've got a negative velocity. So the distance from the origin is decreasing. It's going towards the origin at the moment. But the acceleration is positive. And the effect of positive acceleration has on a negative velocity is that it's taking that velocity closer to 0. So it's a decreasing, but the velocity is also decreasing at the moment because the acceleration is positive. So it's actually a decreasing function with a decreasing rate. But as soon as, and you've got to be careful of this, as soon as it passes the origin, if it's still got a negative velocity, now it's an increasing function. But the rate's still decreasing. And as soon as this velocity becomes positive, if acceleration stays the same, now it's an increasing function at an increasing rate because the velocity becomes positive and starts to grow. So it can change depending on your position. So in terms of descriptive terms, that's quite hard. Another way you could do it is just actually represent. So we've got our displacement is there. Our velocity is backwards -7. Maybe I'll do it a bit more to scale. And our acceleration is +3. And you can use that to help you guide you on what's happening. If they're one each other, that usually promotes an idea of decreasing. So this is a positive displacement with a negative velocity. That implies a decreasing position. It's a positive acceleration, negative velocity. That implies a decreasing velocity. So you've got to be careful and thoughtful about your language that you use. As you're doing questions here, think about that language and think about how it applies to the graphs that you draw. Are there any questions on that? The first, if you get something like this, and I think there's some questions like this in the exercise, the first thing I would do is build a representation. And because it's one-dimensional movement, that's going to be probably just a number line based representation. But then once you've got your position in that number line, you can start to think about the effects of velocity and acceleration on that position. And then you can start to build a statement about what's happening at that point in time. Here's example 2, much more likely to see in your exam. Something like this. A marble is rolling on a curved track such that, now you're not going to often get motion that is a square root function like this. But of course we can design the curved track however we like. So we could make a curved track to allow for this motion. But who cares about that? Sometimes you'll get questions where the context doesn't make a lot of sense. Here's our function, x is displacement, t is time. Calculate the velocity when t equals 2. How are we going to do that? So I heard this, I heard a couple other things as well. The velocity equals dx dt. And dx dt is equal to the derivative d dt of t squared plus 2 to the power of a half. So I derived that. This is the chain rule question. You can do the long version of the chain rule if you want, but I'm just going to break that d to t question. So the half comes out the front. I get t squared plus 2 to the power of negative a half, and then I multiply by the derivative of the inside function, d dt of t squared plus 2, which is 2t, and you can skip that step if you want to, but I'm just sort of showing this, breaking it through the question. Negative a half times 2t, and that of course simplifies down to be, I'm going to write it like this, t over, because it's a negative power, the square root t squared plus 2. But if I have to find the acceleration later on, it might be better to write it as t times t squared plus 2 to the power of negative half. Because that'll be the one I can derive later on to get acceleration if I need to. Leave it at that. At t equals 2, I get this. V equals 2 over the square root of 4 plus 2. That's equal to 2 over root 6. If you go back to your work in year 10, about the end of term 1, start of term 2, we probably shouldn't leave surds in this form. We should rationalise the denominator. If you put that in your calculator, it'll probably do it for you, and we're not testing your ability to rationalise the denominator, but we end up with 2 root 6 over 6, which is root 6 over 3, and that's root 3 over 3. There we go. Any questions on that first one? You just need to, yeah, everything here is not, none of this is new. This is just 2 or 3 processes put together that you know. So you can do those processes. Calculate the average velocity in the first 5 seconds. How do we do that? So B, find V and V at 5 seconds. So hopefully you can see V0 is equal to 0 over the square root of 0 squared plus 2, which equals 0. So the initial velocity is 0. And V5 is equal to 5 over the square root of 5 squared plus 2, which equals 5. Sorry? 2 over 2 squared. Because...
No, wait. Yeah. 2 root. No, wait.
T is 0, you put 0 in there. And to be honest, I don't mind. Okay, 5 over root 27. Root 27 can be written as 3 root 3. So that can be written as 5 root 3 over 9. So that's it in rationalised form. Yep. Take out. Well, the 5's already outside the set. What do you mean here?
Yeah.
Not while they're added together. Okay. If it was 5 squared times 2, you could take it out, but 5 squared plus 2, you've got to evaluate first. So there's V values, and my average velocity is equal to so velocity is equal to displacement over time. So it's equal to, can we see what I've just done wrong? I've not done anything wrong, I've just done something I didn't need to do. Right? The average velocity equal to? Velocity is equal to change in position over change in time. So displacement over time. I've not calculated my displacements, I've calculated my velocities. I didn't need my velocities. Now, it should work out that if I get this and divide it by 5, that should be my average velocity anyway, but is the overall change in position divided by the overall change in time. So what I should have actually done was calculated. So I'll leave this here and put that through it. What I actually need is x0 and x5. So I apologise about that. X0 and x5, x is the square root of t squared plus 2. So x0 is root 2 and x5 is root 27, which equals 3 root 3. And so my change in position over change in time is 3 root 3 minus root 2 over 5 minus 0. And there's not a great deal I can do with that. 3 root 3 minus root 2 over 5 meters per second. There we go. So don't forget, average velocity is actually displacement over time. So you've got to find your displacement at those times. Just to show you what I mean, this function, square root function, so it's going to look something like a square root function, but it's got an internal, so it looks like this, like that. And this point here is time 0 and position root 2. And this point here is time 5 and position 3 root 3. And the average velocity is the gradient of this line. And to find the gradient of that line, I do change in change over change in time. So that's, and I just went wrong. But you got the formula for that, so just remember you got to find x0 and x5. That's that one, that's that one. What's the acceleration when time equals 2? How are we going to do that? Second derivative, excellent. So velocity, or actually let's write this down. Acceleration equals dv dt, which equals d dt of the velocity left in that form, t times t squared plus 2, power of negative a half. How do I do that? product rule, excellent. So this is on the outside, there is a chain rule component, but that's my V. And V has a chain rule element inside of it. And this is my U substitution there. So I need to do the product rule now. U equals T, V equals T squared plus power of negative a half. U dash equals 1, V dash equals negative a half, T squared plus 2 to the power of negative 3 over 2. I've dropped it by 1, multiplied by the derivative of the inside, which is 2t again. And that simplifies down to be negative t squared plus 2 to the power of negative 3 over 2. Having fun yet? And the product rule is u, v dash, v, u dash. So it's, or u dash v, which is just t squared plus 2 to the power of negative a half, plus v dash u, which is t times negative t times t squared plus 2 to the power of negative 3 over 2, which can be simplified to be t squared plus 2 power negative a half plus, not plus, minus t squared times t squared plus 2 power of negative 3 over 2. And at time equals 2, a is equal to 2 squared plus 2 to the power of negative a half minus 2 squared times 2 squared plus 2 power of negative 3 over 2. And now I just need to evaluate this. And it's getting to the point now, I'll work it out as a surd. You might calculate it in your calculator and give me a as well. But this becomes 1 over root 6 because the negative a half, that's 6. The half is the square root. The negative makes it 1 over the square root. So don't forget those index laws. And then I get minus 2 squared times that stuff there is 4 times, and it's 6 to the power of 3 over 2, which can be written as the square root of 6 cubed. That's what the power of 3 over 2 means, but it's actually 1 over that. So I rubbed it out and I put 1 over the square root of 6 cubed. So it's getting a little bit complex, but I'll fix this up now. Minus 4 over 6 root 6 is what that would look like. And then you might work that in your calculator. If anybody's done it on a calculator, it should come out as 3, it should just come out as 1 over 3 root 6, I think. Have you done that, Chris? That'd be a great Year 10 surge question. Anyway, that's part C. How do we find the average acceleration? We're on part D. Average acceleration is the gradient again, and that's equal to change in V over change in T. And so if I go to my average acceleration, I need the change in V is between, notice here my domain, between 2 and 5. So I need to find V5 minus V2 over 5 minus 2 because my change in time is 5 seconds minus. V5 I accidentally found earlier. There it is there. So let's use that, shall we? V2 I also found earlier. It was my first question. So it's there. So Ed, you're listening intently. Can you remember root 6 over 3 for me? You got it? Excellent. Harvey, 5 root 3 over 9. Harvey, what is it? No, you don't have to work it out. It's all right, I'll remember it. Ed, what was yours? And minus 2 is 3. Have I done that twice this lesson? Good times. Okay. Now I can simplify that down to be 5 root 3 minus 2 root 6 over 9. And by 2 root 6, I mean 3 root 6 over 3 times 5 root 3 minus 3 root 6 over 27. And I might be able to simplify that down more. I don't think I can. So that'll do. We're there. What's wrong? Oh, good. Thanks. And lastly, question E, and I can see some people probably need me to stop. So, when the marble has constant velocity, what do we know about when the marble will have constant velocity? The acceleration needs to equal 0. So, acceleration function, the question says when, so I need to work out when this equals 0, which looks scary, doesn't it? Paste that, that's my acceleration, and I need to work out when at what t does a equals 0, that's constant velocity, so I want t squared 2 power of negative a half minus t squared plus 2 power of negative 3 over 2 equal 0. Now this is going to seem, this looks pretty scary, doesn't it? It's actually pretty easy though. Can we show you how? Why not? Let's divide it by t squared plus 2 to the power of negative 3 over 2, first of all. So this is high-end simplification. That's going to get rid of this horrible thing, because to me, this is the horrible thing here, this square root. But both of them have a square root thing in here. So I'm going to divide it by that, and that will give me t squared plus 2 power of negative a half over t squared plus 2 power of negative 3 over 2 minus t squared plus 2 negative 3 over 2 over t squared plus 2 to the negative 3 over 2. What's 0 divided by t to the negative 3 over 2? 0, good. So that's just equal to 0. What happens here? They cancel out. Here, index law tells us if we've got the same thing but with powers, we subtract the powers. What's negative a half minus negative 3 over 2? 1. T squared plus 2 to the power of 1 minus t squared. You see what just happened? So this becomes t squared plus 2 minus t 2 equals 0. What does that mean? That means that this is now a contradiction. The object is never at a constant velocity because acceleration never equals 0. Okay? Good. Now we did divide through by this, so that factor there, we've got to be a little bit careful. That factor could equal 0 and still work. So if t was the square root of 2, no, if t was, yeah, for this to be 0, t would have to be a complex number, which is specialist math stuff. So that's not going to work. So yeah, that's perfectly fine. An acceptable answer. There we go. So that's about as hard as it gets. And I know you might be thinking, yeah, but that's pretty hard.